Okay, so let's go over handout 19 here. The first thing I want to talk about is this motional EMF situation. Um, why does this bar end up with an induced EMF? So let's talk about that first. So if you can imagine this bar is full of free electrons. Okay, it's full of free electrons because it's a metal, because it's a conductor, and the entire bar is moving to the right. Therefore, these electrons are moving through a magnetic field. And as we've discussed, if you have a charge moving through a magnetic field, it will experience a force, QV cross B. Okay, so all of these electrons are experiencing a force from the magnetic field. What's the direction of the force? We have a cross product here, so the direction of the force, we're going to use right-hand rule. Okay, and if you've been watching my video lectures, you may know that I've been calling this right-hand rule number 1 because it's the most fundamental. It's the right-hand rule that applies to the cross product. Okay. So what's the direction of the magnetic force on these electrons? So I need to use my right hand. My fingers, V comes first in the cross product, so my fingers need to go with V. And then I need to flip my hand so that the magnetic field lines are coming out of my palm. So my hand ends up like this. I'm twisting as much as I can here. So my thumb ends up pointing towards the bottom of the page. So these, but the Q is negative here because we're talking about electrons, right? So I have to flip my answer. So the force is going to be up. So the force, magnetic force on the electrons is up. So that means the electrons are going to congregate up here at the top of the bar. Okay? And they're going to leave positive charges behind down here. And so what have I done here? What has the magnetic field done? It has separated negative and positive charges. And if you think about it, that's exactly what a battery does. It uses a chemical reaction to separate positive and negatives. Here we used a magnetic field to separate them. So this is effectively like a battery now. And if I connect the positive end, so this is the positive end down here, negative end up here. If I connect the positive and negative end, I'm going to get a current. I'm going to create a circuit where this bar is acting like the battery. All right, so what is the voltage of this battery? Or in this case, EMF, which EMF is measured in volts. So when you see EMF, you can think volts. Okay, so what's the magnitude of the EMF? Your book goes through this calculation, but the EMF, I use script E for EMF. I think your book uses lowercase EMF, is equal to V, which is the velocity of the bar moving to the right, times B, the strength of the magnetic field, times L, the length of the bar. Okay. All right. What's the direction of the conventional current? Well, if this is acting like a battery, we know that conventional current comes out of the positive end of the battery and goes towards the negative end. So the conventional current is going to go this way. So it's going to be going up through the resistor and down through the bar and then back up through the resistor. So it's going clockwise, right? So the direction of the current, clockwise. All right, what's the magnitude of the current? Well, as usual, we're going to use Ohm's law because we know the voltage, right? The EMF in this case, and we know the resistance, R. So the current is going to be the EMF divided by R. So that's going to be VBL over R. All right. And then lastly, what is the magnitude and direction of the force you have to apply to keep the rod moving? So let me talk about why there's a force required on this rod now. So some of you may remember from the reading that if I take this resistor away so that these bars are not connected, and So the rails are not connected. And I move the bar. Once it starts moving, it'll stay moving. However, if I connect this into a circuit, that changes. And the reason that changes is because now I have a current. And that current is going through this bar as it goes around clockwise around this loop. So by connecting the rails, I've created a current in the bar. And now I have a current inside a magnetic field. And as we've discussed, a current, which is made of moving charges, is going to experience a magnetic force. All right, so here's the formula for that. So again, we can use right-hand rule to find the magnetic force on the current. Notice there's no velocity here. So this would be true even if the bar was at rest, as long as there was a current going through the bar. Of course, there's no current if the bar is at rest anyway, but it just depends on the magnitude of the current, the length of the bar, and the magnitude of the magnetic field. What's the direction? So we're going to use right-hand rule. The direction of I comes first. So I need to point my fingers in the direction of I. I'm focused on the bar only. So my fingers need to go towards the bottom of the page. Okay. And then I need to rotate my hand so that the magnetic field lines point out of my palm. The magnetic field lines are coming out of the page, so I need to rotate my hand so my palm is pointing out of the page. And my thumb is to the left. So this current is going to experience a magnetic force to the left, which means if this bar is already moving, it's going to be slowing down because this force is going to oppose this velocity, this motion. If I want this bar to move at a constant speed, what should the net force be? Well, we talked about this a lot last semester. If V is constant, then that means, if and only if, it's true both ways, that means that the net force is 0. So we have the magnetic force to the left, and I need the net force on this thing to be 0 for the bar to move at a constant speed. So I need to pull the bar to the right with some, I'll call it FE, external force. It doesn't matter what provides the external force. You could grab the bar and pull it with your hand. You could tie a string around it and pull it. It doesn't matter. But if I want this thing to move at a constant speed, I need to have equal and opposite forces. So this force is going to be to the right. What's the magnitude of this force? Well, it's going to equal the magnitude of the braking force, right? The one that's trying to slow it down. And so what is the magnitude of that force? So the magnitude of that force, which is going to equal the magnitude of my external force, so that they're equal and opposite, is going to be magnitude of I, magnitude of L, magnitude of B, times the sine of the angle between them, between L and B, between I and B, which is 90. Okay, sine of 90 is 1. So it's just ILB. And in this case, we already figured out what I is. So I'm going to plug this in for I right here. And I get L and B times L and B. So I'm going to get V, B squared, L squared over R. Okay, there's number 1. Any questions? All right, number 2. I have this current that's going around this rectangular loop in this direction, which is, if we're looking down at the loop, it's going counterclockwise. If we're looking at the loop from above, that is, this current's going counterclockwise. And the question is, well, it's in a magnetic field, so the question is, what are the directions of the magnetic forces? So we're going to use the right-hand rule. And we're going to use it on each of these 4 segments. And the reason we have to use it separately on each segment is because in each segment, the current has a different direction. Right? So there's going to be 4 different directions of magnetic force as well. So I'll start over here. I'm going to make my fingers follow I, and I need to rotate my hand so that the magnetic field comes out of my palm. The magnetic field, the way it's drawn here, basically means it's coming out of the page, right? So I'm going to rotate my hand so that the magnetic field's coming out of the page, and my thumb is pointing perpendicular to the current. Right, so there's a magnetic force. by the way, I mentioned this in one of the videos, but I'm gonna mention it again. If I have a cross product, A equals B cross C, then we know that B and C are both going to be perpendicular to A. That's the nature of a cross product. So if A equals B cross C, then I know that B is perpendicular to A and that C is perpendicular to A. So if I apply that logic to IL cross B, then I know that the force must be perpendicular to the current and it must be perpendicular to B. Okay? So this is a right angle. It's got to be perpendicular to the current because it's a cross product. Okay, how about this segment? So fingers with the current, palm out of the page. This one is pointing out like this at a 90-degree angle. And so you can see the pattern here. This one's pointing, they're all pointing away from the center, away from the axle. So the magnetic field here has the effect of trying to make this rectangular loop bigger. And it may or may not succeed depending on how strong the magnetic field is. All right, how about the side view? So now we're looking at the same situation from the side. So this current that's going in is this current right here. So you can imagine we're looking at it. So here's our eye over here. Okay, we're looking at it from this side. So we're looking right at the axle, at the end of the axle. And this current is going to be traveling away from our eye. So that's why this is end of the page. And this current is traveling towards our eye. So that's why it's out of the page. Okay, so what are the directions of the forces? So it has to be perpendicular to I and perpendicular to B, right? I is into the page and B is vertical. And so that means it must be like this, right? We already showed that it's pointing away from the axle. But in order to be perpendicular to I and B, it's got to point like this, not like this. Because this is not perpendicular to B. Okay, so FB. And then up here is pointing away. It's got to be perpendicular to I and B. All right, so that's the answer to part B. How about part C? Will the loop rotate? And the answer is the loop will rotate if there's a torque around its pivot. Is there a torque around its pivot? Well, we did this last semester too. I'm going to take this force, I'm going to divide it into a piece that's parallel to the axle and a piece that's perpendicular to the axle. So I'm going to draw the perpendicular. Can you see that okay? The perpendicular force and the parallel force. So as long as there's a perpendicular force, there's going to be a torque. Right? And the torque is going to be equal to this perpendicular force times the length of the arm here. This parallel force has no effect on the torque. It does not apply a torque. This parallel force is basically trying to stretch the bar or the wire loop. This one's causing a torque. Over here, I can make the same analysis. So I've got the parallel. Let's see. So F parallel, F perpendicular. And this is applying a torque also. And notice that these torques are both applying a counterclockwise torque, right? This one's causing this point to move this way. This one's causing this point to move this way. All right, so this is counterclockwise. All right. Now, let's redraw this previous situation, but where the loop is horizontal. So here's my axis, okay? And I have this current going in. I have this current coming out, and B is towards the top of the page, like before. So the only thing I've changed is I took this seesaw and I balanced it. So that's horizontal, okay? So what are the directions of the magnetic forces now? Well, here, I is into the page, so fingers go in. B is towards the top of the page, so I flip my hand around so my palm points towards the top of the page. And my thumb is going to the right. That's the force of the magnetic field on that current. Over here, fingers come out, palm points towards the top of the page, my thumb is pointing to the left. Do these forces cause a torque? And the answer is no, right? Because they do not have a component that's perpendicular to the arm of the lever arm here. It has to have a perpendicular component in order to apply a torque. This one is exactly parallel, and so is this one. So the effect of these is to try to stretch the wire loop. Okay, any questions?